Hello, and welcome to Setting the Standard, the podcast about wireless radio standards creation from the Wireless Innovation Forum. I'm your host and Communications Director of the Forum, Stephanie Hamill. In this episode, I'm talking about ESCs with Andy Clegg, Forum CTO and Chair of SSC Working Group 1, John Glossner, Chair of the task group assigned to work on the ESC Impact Technical Report, and Mark Gibson, Vice Chair of the Forum and ESC Network Operator. Hi, gentlemen. Thanks for joining me today. Today we're talking about the ESC Impact Technical Report and ESCs. So today I'm going to start with Andy. Andy, what is an ESC and why do they need protection?
Good question, Stephanie. So as some of you may know, in the Citizens Broadband Radio Service, we share the band with the Navy's radar system that mostly operates on ships out in the ocean. As part of our deal with the government and with the DoD, we have to protect those radars from interference caused by CBRS. And the way we do that is we've set up a sensor network around the coast of the United States, pointing out into the ocean, listening for their radar. And when we hear it and detect it, we let the Spectrum Access System know, and the Spectrum Access System reconfigures CBRS devices in the area so that we don't cause interference. The Navy doesn't want us to geolocate their ships to great accuracy because that's, confidential or classified information. And so our ESC networks are designed to only locate the ships to within an area called a dynamic protection area, or DPA. So if you look at that map that's being shown there, that's that set of light blue areas around the coastline of the United States with the separate DPAs separated by white lines. And so we set up our ESC networks pointing into those DPAs, and when a radar activity is detected in one of those DPAs, we let the Spectrum Access System know which DPA, and the Spectrum Access System rearranges CBSDs in the areas along the coastal areas around those DPAs. So one of the things to keep in mind about an ESC is, again, it's this network of sensors. There's a few hundred total when you include all of the ESC networks that are operating in the United States today. There's a few hundred sensors total among all of the networks. And those sensors themselves have to be fairly sensitive because you may not be able to tell from the scale of the map here, but those DPAs extend beyond about 200 kilometers off the coast of the United States. So if you have a sensor on land near the beach pointing out into the ocean, it's got to be able to detect a radar that could be as far as 200 kilometers away. And even though these are high power radars, 200 kilometers is a large distance. And so these ESCs, their sensors need to be quite sensitive in order to hear potentially distant radar activity. And these radars operate in the exact same band that CBRS is. That's why we have to protect them. And so the ESC sensors have to be listening in the same band as CBRS. So the challenge is, if you put a CBRS device, a CBSD, too close to the ESC sensor, it will interfere with the sensor's capability to hear these radars at the edges of the DPAs farther away. So we have to constrain deployments of CBSDs and keep them away from the ESC sensors in order that they not cause interference to the ESC sensors. And so what it creates is what we call a whisper zone. It's a name that we just invented for this, but it's basically that zone around an ESC sensor where you can't put CBSDs, or if you do put a CBSD, there have to be some constraints, like it can be lower power or pointing away from the ocean or some other constraint to keep it from causing interference to the ESC sensors. So the existence of these whisper zones impacts the number of CBSDs you can deploy along the coastline. And we're looking for solutions to get around this challenge.
Okay. So, John, I'll come to you next. What work did the task group do to evaluate these ESC impacts?
So the first thing that we looked at was what is the model of the ESC sensor, and NTIA has code for doing that and analyzing the distances and everything, and the antenna patterns and the locations of the sensor and what its impact would be. So if you take a look, so basically you put in the antenna pattern and a bunch of physical properties about the ESC sensor itself, and then it computes if a DPA is adequately covered and to within some statistical reliability point. As Andy mentioned, it does go further out, but there's 2 zones that this software comes back with. So given that, and given that what the impact, the ESC impact sensitivity is within that DPA, then we came up and tried to figure out, well, how can you locate an ESC sensor with minimal impact to a CBSD? And also we had to discuss, well, what does it mean, impact? How do we measure it? And then how do we validate it? And it's a little bit complicated because there's some subtleties about the antenna patterns that are transmitted by the SASs don't necessarily have to be the NTIA model, but they have to guarantee that the ESC is protected. So we came up with a number of ways of doing that. And for today, I'm just going to describe one very briefly. So we tried to take this antenna pattern and then partition it up into what we called pixels. We set a CBSD right in the middle of the pixel and pointed it directly at the ESC sensor. And then we looked at how many people within that area would be impacted by an ESC sensor. And then we summed it up over all the areas. So that was the first metric that we used, and it seems to be the most intuitive metric that we came up with. So if you were to locate a CBSD within that area, what would be the impact of the population, or how many people wouldn't be able to get coverage? It is a kind of a worst case conservative analysis, and there are some other kind of extenuating issues to look at that might make this, a little bit of too conservative an approach. But it's very intuitive and it seemed to work pretty well. And we looked at all of the DPAs, the coastal US DPAs. When we did that, we had software which was donated by Google. It covered actually more than just this method of computing impact. And so the report covers all of that. It's available on the Wireless Innovation Forum's GitHub site. And it included 148 ESC sensor locations from multiple ESC sensor network providers. They were aggregated and anonymized, and that covered the whole, contiguous 48 DPAs. So when we looked at that, what we found is the vast majority of the time, there were not that many people affected. Like less than 5,000 were 80 of those 148 ESC sensors. But there were some that had pretty large population impacts. And of course, populations along the coast are not evenly distributed. There are some very heavily populated areas, and there are some not so heavily populated areas. So on average, if you looked at those 146 sensors, on average, they were impacting about 21,000 people, but with a pretty large standard deviation of 45,000. So we ran all those numbers for all of the different algorithms that we had, and we put them together into this report. And so you can get advice on, maybe how to best locate an ESC sensor so it has minimum impact, and then see for the sensor networks that we looked at, what were the results of checking all of those sensors for interference.
Great, thanks, John. Mark, what does that mean for CBRS?
Well, this is part of the reason we undertook this study was for 2 things. One is, and Andy and John both touched on them, but just reiterate and underline or amplify. One is we were aware of the issue of the ESC susceptibility and interference, but we've never really quantified it. It was a lot of folks saying, well, this is sort of the nature of these very sensitive sensors that could be interfered with, but we really didn't know what it looked like. And so by virtue of the effort that we did, we were able to quantify that and literally quantify it. We can say in any location with really good metrics, here's what it's going to look like. The other thing we got out of that, or the other action or benefit, was now we have a set of best practices, because that was the other thing that was driving this, was to develop some really good best practices for ESC siting, antenna orientation and antenna design, and just general, the way you deploy it. And the idea was that we knew that when we went into this, there were two, maybe three ESC providers, but the commission has appointed or identified a total of 9 SaaS providers. And there's others that could be coming on later with ESC. So we want to try to come up with a best practice so that the whisper zone that Andy and John mentioned problems don't get any worse. So what it means for CBRS is that now we have a good way to quantify the problem. We have a good way of mitigating the problem, and that's really what we were trying to accomplish.
Okay, and what about adjacent channels?
We didn't look at that in the study. There has been some work done. I think Andy did some work on looking at the adjacent band below. The adjacent band above isn't a problem, which is the new 3.7 gig service band that was auctioned this year for $81 billion. But that's 50 megahertz away from where the sensors operate. But there was a concern about the 3.45 gig band, which will be auctioned starting October 5th. Because of the nature of the high-powered operation in that band, higher-powered. Base stations in that band for a 10 meg channel can operate in rural areas up to 32 kilowatts, compared to the 50 watt of the Category B devices, CBSDs and CBRS. So there's a huge mismatch. And just general, based on the modeling, is that it could be 3 channels adjacent to the bottom of the CBRS band that we have to worry about that. So that's a concern. And we are working within the Advanced Technology Group of coming up with procedures, our Advanced Technology Committee, coming up with procedures for coordinating with new 3.45 gig service licensees.
Okay, great. And are there alternatives to ESCs?
There's always alternatives to ESCs, and there's a couple of them being considered right now. And in fact, one of them we built, it was probably at least 4 years ago. Andy and I worked on it. Andy did most of the coding work, but it was essentially, we built a portal. Model off of some of what we had done before in other bands, which essentially allows the DoD on a set of ground-based radars to just tell us very basic information on how these things operate, location, and all they had to do is pick the location from a drop-down box, and then just sort of the tempo of the operation, start and stop time, or start time and duration, and then finally frequency. So very basic information. They can enter this information into this portal, and that information then gets fed to SASs, or is available to SASs to read. And then once we look at the data on that portal, we will know that for any given, these are inland radars, to not operate consistent with what's in the portal. So the DoD has taken that concept a little bit further, the very same concept that we developed, and actually have been able to apply to American Samoa. In addition to the 11 ground-based radars, they've taken that concept and put it into a program they're calling TARDIS. And TARDIS is an acronym that escapes me right now, but basically it's it's a larger program, but there's an aspect of that which is essentially the same thing. It's a spectrum selectability portal that allows the DoD to do exactly the same thing for exactly the same areas. It's a little bit more funded. And one thing the portal that we developed does not do is deal with some of the classification zones related to dealing with classified information, of which there's more than one. So when the TARDIS program, the S3 part of it, comes out, it will be able to properly identify and mitigate any transfer of information across these zones, which we really couldn't do. And that's one of the main reasons that while our portal is being used a little bit for American Samoa, it's not been broadly used because of concerns about of those zones. So the DoD is doing one, and then NTIA is doing something too that they're calling the Informant Incumbent Capability. Or they actually call it incumbent informing, but we can't say it that way. It doesn't make any sense. So we call it informant incumbent capability. And theirs is a little further down the road, and theirs is a much broader scale or scope. They're building this more to accommodate all of the potential sharing to rather than have to build an ESC for future, we could use these portals. So while the IIC the commercial availability of that, or not commercial, but the availability of that is sometime in the next several years, whereas the TARDIS S3 should be available, we're hopeful that in the near term being by the end of the year. So there's several different types of portals. There's really three. There's the IIC that NTI is developing, there's the portal that we developed, and then there's the S3. So there's lots of alternatives to the ESC, none of which will cause interference or be susceptible to interference for CBSDs.
Great.
And go ahead.
No, I was going to say, Andy or Mark, what are the roadblocks then to implementing the IIC?
Yeah, I mean, roadblocks. Let me first speak from the SAS side. There are no roadblocks. In fact, as Mark pointed out, we already have a portal we designed, but that only protects a few inland test R&D sites. It doesn't protect the ships out on the coast. And they adopted this for American Samoa. And we actually got from when the DoD decided to protect American Samoa this way to actually being able to provide SAS services in American Samoa, because we didn't have to deploy an ESC. We got from 0 to full deployment in 60 days. If you have to deploy an ESC, it would take a long time, because you've got to build network infrastructure and things. So from our perspective, there's no block. We're ready to go. We can use IIC immediately. On the government side, there's a few roadblocks in the way. The main one is this is a change in the way that they operate. Right now with the ESC sensors, they don't, when they're out on the ship and they turn the radar on, they don't have to worry about anything else. We sense them and we avoid them. If you switch to IIC, there's like one extra thing they would have to do, and basically click a mouse button or something and indicate that they're operating. And that would proactively inform the SASs. Instead of us sensing the radar, they would just basically tell us when and where they need protection, and we would protect them. But that's a change in the way that the DoD operates. And of course, anytime you talk about changing the way the DoD operates, that could require training and a long time scale to implement and things like that. So really the roadblock is the change in the concept of operations for the DoD, combined with the time scale. As Mark mentioned, at the moment, they're looking at several years before they get IIC off the ground, and even then it's not really the full-blown IIC with all of the ships connected and things like that. So I think between the change in the concept of operations that the DoD would have to implement, along with the time scale and the funding, of course, because funding is always an issue with the government, and the funding, it could be many years before this gets off the ground.
Okay. All right. Well, all of this is just really touching on information that's going to be expanded on in our November event. And you'll all be putting that on, and I'll include information for people to have access to that. So very exciting stuff. Thanks, gentlemen.
Thanks, Steph.
Thanks.
And you have a great day, and I'll talk to you again soon.
Okay, thanks.
Bye.
Bye.